Hey guys, Luke here again, and we're going to talk about more silicon chemistry. In this, we're going to talk about alkyl silanes and also allyl silanes, providing the video isn't going on for too long. So, the synthesis of an alkyl silane is done via this repair mechanism. So, we did this earlier, where you use lithiums, you use two equivalents, etc., etc. Just drew the mechanism on in rough of what effectively happens. Obviously the lithium binds in this position here, goes through that, removes the tosyl group. Tosyl group being this, the R being obviously what you've got here, tosyl part being this SO2 with a benzene ring and a methyl group there. In this step, we've pretty much done both steps in one. We've removed N2 and we've also removed SO2 minus. As I said, I did a little mechanism quickly sketched there. It's just a rough one. Like I say, we've done it before in one of the other videos. Adding in Me3SiCl, and that just displaces the lithium in this case. And that's the product. So an alkyl silane is where the double bond is one away from the silicon. So we move on to the alkyl halides, which is another way we can form these alkyl silanes. Effectively, it's really simple. We add the lithium like usual to remove the bromine, acts as a good leaving group. We get the lithiated form, and then we just add on our silicon group there. So the reactivity of this, it's all dependent on the stabilization or the stability of the beta cation. An example of this is reacting it with I2. Alternatively, you could probably react this with Br2 as well, or a diiodo or dibromo complex. Double bond attacks the iodine or bromine and then kicks the other one out as well. And then we form a cation, the beta cation here, which has to undergo bond rotation. Obviously there's an empty pi star orbital here, and the Si needs to be in plane with that so it can donate some electron density to it for stabilization. Next up, we get this product here. It's effectively what we've got. The SiMe3 just donates back into the double bond, and then we've got that. This is, as it says here, very stable. We've just got a I minus, and from this stuff up here, got the I minus from this stuff up here, and we've got SiMe3, which is a driving force for the reaction. Another is acylation. In this case, we're going to start off with a chloraldehyde, I don't know, but that's going to attack AlCl3. Next up, we've got the triple bond O here, which is obviously making it, the chlorine leaves, should I say. And then we've got the triple bond O with a CH3 there as well, which is literally this, with a triple bond. After that, we've got our alkyl halide, attacks the triple bond and then neutralizes the charge. And then we've obviously got AlCl4 minus. We need the bond rotation to stabilize this carbo beta cation, and that just rotates to be in the same plane, so obviously we want that facing backwards. And then, as I said, as seen above, what happens is we just remove the SiMe3, that donates it back into the bond, and we've got our product, which is essentially double bond there, we've got our newly formed bond with our oxygen, and then we've just got a double bond there, like I said, and that's pretty much the product. Now on to allyl silanes. Allyl silanes are slightly different to alkyl silanes, in which case you'll see very shortly. In this case, we can do this using the Peterson synthesis. Add yourself Mg in using diethyl ether. That obviously just adds next to the I there, making a sort of Grignard. Obviously, being a Grignard, it can then attack the ester here, the double bond of the ester, which then is able to effectively kick off this OMe, and obviously because we've got our silicon group there, that attaches to where the OMe was kicked off. Next up, we're going to use another equivalent of this. As it says here, we've got two equivalents. Next equivalent, we just do exactly the same thing again. Curly arrow there, attacking the ketone now, and putting the electron density on top of the oxygen. And then obviously we want to get rid of the oxygen. Now we've got two silicon groups, and this is the Peterson step here. And what we do is we remove one of our SiMe3 groups. In this case, we're going to remove this one here. Just donates the electron density back in, forming a double bond, and then we lose our oxygen as well. We can also form this by the Wittig reaction, which is a longer process, but some may say slightly easier. So the Wittig reagent here is something you'll have to remember. It's H2C minus, and then we've got a triphenylphosphine attached to it with a positive charge. Basically an SN2 reaction. This part's obviously fairly easy. Just add in the triphenylphosphine and remove the iodine. Once we've done that, we've got I minus in the product there. The H explicitly drawn because that's the one we're deprotonating with our butyl lithium. Once that's removed, we've still got a positive PPH3. What we're going to do is we're going to add this just as a random ketone. It can be any sort of ketone. It's going to form this intermediate here. How it does that is that the negative charge attacks the double bond. The double bond breaks, and then it forms a bond with PPH3 to form this cyclic structure. And then after that, we have a retro 2+2 effectively, where what happens, I don't know if I've got my pen now. I hope I've got my pen. I don't think I've got my pen. Okay, so what happens is we have electrons go up like that, and electrons basically go down like that. Break that bond, we get O, double bonded O to triphenylphosphine, and then we get the product as shown below. Some reactivities of this reaction, as you can see, there's plenty of reactions here. No mechanisms in this case. It's important that the silicon stabilizes the beta cation as for the alkyl case. Just as a quick side note, I did say earlier that we'll see what an allyl silane is. Like I said, the alkyl silane is one away. The allyl silane is two or more. I'm assuming. So here's just a quick one. We'll just add an I2 again. Pretty much exactly the same. Although this I adds across the double bond. Obviously the double bond will attack the I and remove it there, forming a cation. And then all that happens really is that the silicon group donates its electrons into a bond to form a double bond. But as you can see here, there's plenty of reactions that can happen. If we're doing it with titanium chloride, Lewis acid, and just alkyl halide, or alkyl halide, we get this product. Obviously we keep this double bond here, but remove the silicon in this case, and then add the R there. In this case we've got an epoxide, it's just a ring opening essentially. Same sort of mechanism as what we saw with the lithium reagents. This case we're adding a chloraldehyde, or whatever I called it last time, and that's effectively the same. We just literally remove the chlorine, remove the silicon, and then it's pretty much exactly the same for the tin chloride and this ketone there as well. I think there's one more. Yeah. This is a kind of major reaction that we can use Alkyl silanes for. It's just a Sakura reaction, or Sakura reaction. Effectively what happens is, well, you can see it right there. It's just a one-step mechanism really. That's a transition state. Tin chloride binds, I suppose, that's something that happens initially. And yeah, the electrons just push out from the silicon and then result in a product here, which is obviously after workup as well, and we obviously lose the tin chloride as well. So this is only partially bound. It should be a dotted line really, I think. But that's it for the silicon chemistry. Up next we're going to look at protecting groups and how they can obviously shield certain groups like nitrogen and oxygen in reactions.